If you examine the two structures in this computer model, you can see that they're stereoisomers. They have the same formula and same bonding connectivity, but they can't be superimposed on one another. If we bring them together, everything matches up except the positions of the chloro and the fluoro atoms. So how are they related? That's the next thing we want to know. A pair of stereoisomers are either enantiomers or they're diastereomers. What we need to do is to try to see if these are related as an object and its mirror image. And so what we can do is rotate one of the molecules relative to the other to see if we can find that they're related as mirror images. If we rotate the molecule on the left about what's called the y-axis, we can indeed see that these two structures, although they may not have appeared that way initially, are in fact mirror images. Now we can see a mirror plane separating these two. So in the example that we just saw, we were able to do a rotation of one of the stereoisomers to bring it into a position where we could see that it was related as a mirror image to the first stereoisomer. Two stereoisomers that are related as mirror images are what are known as enantiomers. A pair of stereoisomers that aren't related as enantiomers must be diastereomers. Let's take a look at the cis and trans 2-butene examples shown here. If you look carefully at them, you'll see that they have the exact same connectivity, but they're definitely not superimposable on one another by a translation. So we know that they're stereoisomers, but what kind of stereoisomers are they? There's no way to take the molecule on the left and rotate it and bring it into a mirror image relationship with the molecule on the right. So they're not enantiomers. Therefore, they must be diastereomers. Here's a flowchart we can use to determine how a pair of structures with the same formula are related. The first question we ask is, do they have the same bonding connectivity? If the answer to that question is no, those two structures are constitutional isomers. If the answer to that question is yes, we need to try to rotate and translate one of the structures to see if it's superimposable on the other. If it is superimposable, then those two structures are one and the same. They're not isomers at all, they just happen to be two different views of the same molecule. If they're not superimposable, then we're left with a pair of stereoisomers, and we need to determine what kind of stereoisomers they are. If those stereoisomers are related as mirror images, then we've got a pair of enantiomers. If those stereoisomers are not related as mirror images, we can't rotate or translate in a way to show a mirror image relationship between the two, then we're dealing with diastereomers. Okay, let's put that flowchart to work, first with the example that's shown here. Carefully compare them, you'll see they have the same connectivity, but are they superimposable? For that, a three-dimensional model will help us out a little bit. For the molecule on the right, the methyl groups are both coming up. We'd say that's a cis relationship. The methyl groups are going in opposite direction. We'd call that a trans relationship. So if we color the molecules by their structure and try to superimpose them, those methyl groups, the one particular on the right-hand side of those molecules, are not able to be superimposed on one another. So the answer to this question is no. These are stereoisomers. What kind of stereoisomers are they? I'll leave it to you to decide that there's no way that you can rotate one molecule relative to the other to bring them into mirror image relationships. The answer to that question is no. These are diastereomers. In the next example, the pair of structures can be made to superimpose on one another, even though they may not look that way initially. We're going to take this structure and rotate it by 180 degrees. And when we do that flip, now you can see that the two molecules are identical. Here's what it looks like in 3D. If we color the molecules by structure, rotate by 180 degrees, translate, they're superimposed. The molecules are one and the same. In this example, the molecule on the right cannot be superimposed on the molecule on the left. However, when we rotate the molecule on the right by 72 degrees along the axis that's indicated, that's 1/5 of a full turn of a pentagon, that positions the methyl groups so that we can discover a mirror image relationship between the two molecules. This mirror image relationship means that these are enantiomers. Here's what it looks like in 3D. If we color by structure, make an attempt to superimpose by translating, you'll see that some of the groups don't match up. We can rotate by 72 degrees, and not all of the groups are going to overlap. We can separate these two molecules and look for a mirror plane relationship, and indeed in the orientation that's shown, that's exactly what we have. The structure on the left is a mirror image of the molecule on the right. You can see that every position has a counterpart on the opposite side of the mirror plane. These are enantiomers. With practice, you can get very good at recognizing these mirror image relationships.